hourglasses appeared here. Okay, so Susan Tsutakawa will be speaking now, and she's been one of the original members of the Sybil staff and helps get Sybil's funded originally. She's an expert in crystallography, small angle X-ray scattering, and multimodal methods. In the biospace, she's an expert in DNA repair in particular, but other things as well. Susan, please add to that intro.
I will just, I only have 30 minutes, so I won't waste a minute more.
Nope, it's too long. You're an intro. Yes, go.
Okay, so Bettina and Greg have talked about booking a mail-in SAXS Lite, and then they just give you this sort of thing. So I've been asked to sort of dive a little bit deeper. So if you press this button, what you'll get is this window here, which is the mail-in thing. And so if you need to get an account if you don't have an account, and that's you can get an account. I should have instructions on how to do that, but if you wanted to book a slot, you go to this button to the right, you say book slot, and then you look to see, oh, you know, what I want to do. And so, for example, you can see that the September 26th STC SAXS is already filled, and then the next available one time is here, and then you click here. And these dates are the Tuesday before, and you'll be the Tuesday of that week that your protein will be collected, and you hopefully will send us the samples by then. Another thing I want to point out is that there's these very nice tabs at the top, and it provides information on sort of instructions on how to do this, information about it, and also links to at the bottom here, links to additional details, common problems with SAXS statistics, etc. So you have it for high throughput, SEC SAXS, and the statistics here, which shows you common problems in the sample. Okay, so I am going to move to my talk. I wanted to first say that Sybil's, our name is after these Greek oracles who were known to give you a truthful answer to any question. But the trick is that the value of the answer depended on the quality of the question. And that is true for SAXS because it can give you many answers, and you need to know and be aware of the constraints of that answer and your problem. So to sort of back up, so Bettina gave a really nice example of why you should listen to my talk. Hers is a very nice application of the thing. And then this is what you can do after you've done the analysis, such as what Dan provided. And so the basis of the most powerful thing about SAXS is that you can compare atomic models, and it could be individual proteins, nucleic acids, or combinations of protein and nucleic acids, or protein-protein complexes, and you can calculate a predicted scattering curve and compare that predicted scattering curve to the experimental small angle X-ray scattering data. And that is the basis for a lot of what our beamline does, which is trying to get that atomistic information. Because if you get a blob, it's very hard to know how to test that blob. But if you have a model, it's very easy to make mutations or do things that would test whether that model was correct or not. So this allows you comparison of atomic models to experimental data. And I showed you crystal structures, but as a corollary, you can also compare predicted models to experimental data. And but I wanted to sort of give you some caveats to the predicted models, especially with AlphaFold2. And so AlphaFold2 burst on the scene, particularly in December 2020. This is a plot showing the accuracy of the model versus the length. And what you see is that they gave a very good accuracy on the on their predictions. There are some that are below, but I would say it's mostly 90% correct, and the topology is mostly good. And so that was really impressive. But even more impressive was that the accuracy was size independent, and you can go over 2,000 amino acids. I also wanted to point out that AlphaFold2 was the first protein prediction program that used these attention models, which is sort of used to analyze text. So if you can imagine, you have text, we have words that are associated with each other but are in distant parts of the paragraph, and how you connect those two. It's the same with protein, and that's why this is particularly powerful. And so here is showing you over 2,000 amino acid protein predicted in 2020. There are differences here, as you can see in here, but it is mostly correct, and it was an amazing accomplishment. So if AlphaFold is 90% correct on C alpha positions, why should I care about any kind of experimental validation of the prediction? And what I pointed out here is that you may have the correct topology, but there be significant errors in these predictions. And so how do these errors arise? And so I'm going to show you 4 challenges that AlphaFold faces. And first of all, this is sort of a depiction of AlphaFold2. And what it does is it takes this input sequence and it outputs a structure, but in between it creates these MSAs. It also tries to look in the structure database, and it creates these representations, which then are evolved and developed and provide new improved representations, and then this goes into the structure module for rebuilding. So what happens, so you have multiple sequence alignment, you have experimental structure training, and you build the structure. But one of the challenges is what happens if the MSAs have a low sequence depth. And this is a problem for particularly viral proteins. And here I'm showing an example of viral ALK-BH3 and then the human crystal structure, which is missing this region here. And in the prediction, the AlphaFold prediction, it's saying this area is completely disordered. But from the Ponder prediction programs, we can see that there is probably likely a significant order, and this even could be partially ordered. And so what we have seen anecdotally is that when AlphaFold2 doesn't have the depth for its MSAs, it will just predict it as disordered. And that should be something you should be aware of. The other thing is it uses canonical geometry to build the structure. And so here I'm showing an example of a 2020 CAFS target, and the GGTS was 88, which is really nice. It's probably like, it was like a 1.5 angstrom. RMSD2, the crystal structure. But what we see is that the side chains are not correct. And this is showing the active side of the protein. So this is the most important part of the protein. You can see this histidine, it gets it completely wrong. It's at a 90-degree angle, and then all these other residues are disrupted. And the reason why this is important is this protein, upregulation of this protein, can lead to a much poor prognosis for pancreatic cancer patients. And so inhibiting this might be a good therapeutic path. And so you want to make sure that you get the active site correct. And so why is it mispredicted? Well, it turns out that this is in a non-preferred rotamer position. So here's the closest rotamer, and you can see that the preferred rotamer is what AlphaFold2 predicts. And when AlphaFold2 predicts this preferred rotamer, it causes this ripple effect because this histidine is in a strained geometry. It's really packed in there. So if you put in the wrong one, it causes this ripple effect across the whole active site and even down to the main chain. So strained geometry is a problem, and I've seen this with both the rotamers, unusual rotamers, as well as Ramachandran outliers. Challenge 3 is that prediction of stoichiometry is yet to be proven accurate. If you know the stoichiometry, AlphaFold2 is really good. However, if you don't know the stoichiometry, it will predict to whatever stoichiometry you give it. And so here is showing another CAS 2020 target, which is a trimer. And so it does a very nice job with the monomer, but there is no prediction for the trimer. And so that's another thing that, use of SAXS data is very useful to find out what the stoichiometry is, and then also see if there's any problems with the prediction for the multimer. The other thing is, and this is referred to by Greg, is that the predictions are closer to crystal structures than to their conformation in solution. And so here I'm showing you both the data in reciprocal and real space, and you can see that the crystal and prediction are similarly different than the experimental SAXS data. But in this slide here, you which is in real space, you can see how the crystal and the prediction more match each other than to the experimental SAXS data, indicating that the AlphaFold2, which trained on the high resolution crystallographic database, is predicting crystallographic structures and not what's occurring in solution. Oops. And Greg mentioned this, and that when we participated in CAF, this was in 2018, over half of the proteins that we studied showed that there was some kind of shifting around in solution compared to the prediction. And you can imagine that we're looking at a subset of proteins that were crystallized. So if you imagine all proteins, many of them will be different in solution than what would be predicted from crystallographic lattice with aggregating solution conditions. Oops, I keep doing the same thing. And so why is this important? And so I make this analogy for small angle X-ray scattering. If a group of scientists wants to know how birds can fly, and they take only the high resolution images, they'll get a very good drawing or prediction of a sitting bird, but it won't really tell you how birds fly. So biologically relevant conformations are not necessarily the most stable or can be captured at high resolution. And that is what small angle X-ray scattering can capture. So I mentioned 4 challenges, and what can small angle X-ray scattering do? So we can validate structures by small angle X-ray scattering. For challenge 2, there's no solution available yet, but you should be aware of problems if there might be strain in your structure. AlphaFold2 will not be able to predict that. Challenge 3, the stoichiometry, again, validate the structures by SAXS. And then challenge 4, predictions are closer to crystal structures than to the conformations in solution. So as Bettina referred to, you can model the structures and to fit the experimental SAXS data. And so there are 3 useful programs that I use to compare atomic structures to SAXS data. These were generated by Mikhail Hamel in collaboration with Dina Schneidman and Andre Sali. And I'll be talking about 2 of these 3. One is the FOX-S, which is good for individual atomic structures or monomer dimer mixes where you can mix and combine and compare. Bilbo MD is good for creating models that are beads on a string. You keep the domains rigid and you allow them to shift relative to each other. This is, you can see that really nicely done in Bettina's talk. Scott will be talking about this later today, so tune in for his talk because there's been a recent advance that they're working on. And then the third one I use is the Alice Mod FoxS created by the Solly group. And it is good for when you have a protein that is not rigid, but the domains are flexing within the domain. And Alice Mod FoxS is good for that. There are other programs available, but I'll be talking about these two programs. Oops. So this is the FoxS server hosted by Andre Solly's group. And this is sort of the entry form, and what you put in is you put in your small angle X-ray scattering data, such as what was created, that Dan created. You also put in your atomic model here, and then you submit the form. And what you get out is an output that looks kind of like this, which compares your atomic model to the experimental data. Pay attention to the residuals, or see where the differences are. You can see that this is greatly varying here. There's also differences here, and you can look at the residuals, which is the difference between the model and the experimental data. And you can see that it's not random, because random would be unbiased through your residual, but there's actually a bias in the thing saying that your model does not fit the experimental data, but it is close. Another value that you want to look for is C2. I don't have this example here, but sometimes there's a range that these are sort of fudge factors. And when your C2 is 4 or close to 4, that really is saying you're really, really wrong. And so just really pay attention to your C1 and C2 fudge factor numbers. So that was sort of FoxS for an individual protein. You can also use FoxS for multiple proteins. And here I'm showing you monomer dimer that we use FoxS. You can see that a single model did not fit the experimental data. Here I refer to Chisquare, which is a metric that compares the experimental data to the model. And when the ideal Chi-square is 1. And so the lower you are, the closer you are to 1, that means the better fit you have. And in this case, you can see that any single model didn't fit, but as soon as you give it 2 models, there's a much better fit to the data. You can see that here also in the green is the single model, and then in the red is the double model. There are still differences, but it's been reduced when you combine the two. And this is really important even if you think you have a monomer, because in Greg's P. furiosus structured genomics study, where they looked at over 50 proteins, 2/3 of those proteins homooligomerized. So that says that cells are using oligomerization more than any of us appreciate. And so this is really useful in the to use FoxS to look at those monomer dimer. I think this data was collected in high throughput, not SEC-SAXS, and so there was both in that data. And so how you would do this with FoxS is that you would compress the all your PDB models and compress them into an archive.zip or .zip file, and then it will output it like this, where you have the fit to all the individual models here. This is just showing you the best one, but you can click this and get additional models shown. And then you go over here to the multi-state models by multi-FoxS, Oops, I didn't take a screenshot of that, but I have them all here, and it'll output something that looks like this, which is the trying to do some combination. In this case, there is an improvement with the models that I gave it, there's only a slight improvement in the chi-square. So there's still some problems. But this is how you would do that. Okay. So the next program, are there any SAXS questions? No. Okay. So the next program I'm going to talk to you about is also an Andre Sale program, and this is sort of causes distortion of the protein. So we're not this distortion. The models that you get out won't have the correct absolutely correct geometry, but it gives you a feeling for the flexibility or the movements that this enzyme will, or that your protein will do. And so to do this, you do the Alice mod FOXS, which is different than Alice mod. So they have an Alice mod by itself. And then this is one that's tied in with the small angular X-ray scattering data. You add in your sequence, and then you'll get an alignment between your sequence and the structure sequence. And then you input in your experimental data. And then generally, in the options, I do it. The default is generate static models that are similar to the input structures. That doesn't sound very interesting whatsoever. So I do. I usually pick the middle, the intermediate probability conformations, which causes some strain to match the experimental data. And then you can do also change your Q value that you use and your profile size, and I just use the defaults. In terms of, you can also do multimers in here. There's a very specific set of instructions that you need to use, and really pay attention to your colons and spaces. And so then you'll submit the job. I forgot to say, you submit your job, and that button is here. And then you'll get an email saying your job is finished. This took about 8 hours to run. And then you can go to this job, and you can see, you can say, they'll say, do you want to look at your data by FOXS? And here is showing the FOXS, what it generated for individual, each individual model. And then you push your multi-state models, and then here you can see that this is the distribution of single models, and you see an improvement when you add the second model, although the chi-square is still high. But you can see how this is extended, and then this one is less extended. Here, it shows you the weight, shows you the relative population, and it's suggesting that 60% of an extended and 40% of a more curled structure best fits the experimental data. And you can see the difference between the green and the red, and that there is improvements, although there's still some issues. And here is one showing you where it really became quite flat when I used 2 different models for the with Alice mod FOXS. So I hope I've been able to show you how you can use atomic modeling to get most information out of your experimental data. And this is not to say that these are the exact conformations, but it's more to convey a feeling of where the conformational population is occurring, and it also provides you testable models. So you can imagine, say, for example, if you had an active site here, these residues here would be coming together, and you wouldn't see that in the crystal structure, which is in black. So this work has been developed a lot by the beamline, and I show the beamline here, particularly Mikhail Hamel working with Dina Schneidman and Andre Sali. And also I'd like to acknowledge CASP. We have participated in CASP, and we have greatly benefited from the structure prediction community. And the work is supported by an NIGMS technology R1, as well as an NCI program project, as well as the DOE IDAT program. Okay, any questions?
I would have one to AlphaFold2.
Yes.
Because is it like the same with AlphaFold1 that if you have just a sequence and you upload a sequence that it's predicting the structure due to crystal structures it finds? Or how is it with AlphaFold2 if you just have a sequence without any further
Yeah,
prediction?
so it obviously, if there's a template, it can take advantage of that template. But if there is no template, AlphaFold2 does an amazingly good job at the prediction. And I could go in a lot more in depth into my theories about why AlphaFold2 is so successful.
Okay.
Yeah, and I forgot to mention that when you do your atomic model, you should make sure that it matches, the sequence matches your experimental data. So if you have a his tag that was not visible in the crystal structure, or not in the you know, the Swiss Prot database of AlphaFold2 structures, you need to add that back in, because the SAXS is picking up that his tag.
But then but then here you have the same case also with the glycosylation. Either you have then to add the glycans to the structure or okay.
Yes. So it recognizes anything that's moving, including the hydration layer, right? It recognizes everything that's moving together as a unit.
Okay. Thank you.
Greg, did I miss anything?
I think you covered the most important points very well. Thank you, Susan, for that. Other questions?
I have a question. So, compared to two conditions, one is that we only have the disordered tail of the protein, and the other one is the well-folded region plus disordered tail of that region. If we run SAXS on both of them, which one give a better sensitivity if the ensemble change? For example, in one solution condition, it will be more compact. In the other solution condition, it will be more expanded. In those two cases, with or without well-folded region, which one is better or more sensitive for SAXS data?
That's a really good question, because you know, if you're interested in the structure of the disordered region, I think that if you're interested in the ordered region, obviously only having the ordered region is best, because that flexibility can mask errors in the ordered structure. But if you're interested only in the disordered region, it would be much better to have only the disordered tail.
Okay.
But it's, you know, we're very interested in how disordered tails contribute to the small angle X-ray scattering data, and the hydration layer of disordered tails will be very different. So it's a very interesting question, and one that we are exploring.
If I can come in on that, I mean, what you're saying is a perfect experiment to run, right? And something you can do with SAXS. You can run folded region, the disordered region, to the two together, And that's something that it gives you the opportunity to do. There are many cases, like we said, of multimers. So you can imagine like a very compact pentamer where there's a huge disordered region per monomer. So what's the structure of that? Like globally, that's just a big hairball, right? So your SAXS data may not be super informative unless you're really interested in the behavior of that disordered region. Maybe it compacts with salt or something like that, right?
Okay, got it. Thank you.
This is an example in a collaboration with Brice Wong, where the monomer is disordered and then the dimer is predicted to be ordered. And you know, we see a suggestion that this might be the case. And in this case, both of them are AlphaFold predictions.
So in this case, we need to use SEC SAXS rather than the high throughput SAXS to do those comparisons, right?
Yes, yes. But at that time, he only had the, averaging. So
Okay.
that's what the data he had.
Got it. Thank you.
But yes, SEC would be best. And I should mention that the scattering is a function of the square of the mass. That means if you have a monomer and it has 1x scattering, the dimer will have 4x scattering because it's the square to the mass. So the dimer, even though it's a low population, will be contributing 3 times more signal than the monomer. So just or 4 times more signal. So just to point that out for when you have different stoichiometry.
Other questions? Got Susan caught us up to time. And the next step on this calendar is to break for lunch at the hour here, or whatever it is you're going to do at your hour. Are there any comments in general, things that we as people addressing questions from our user community should know? Do you have a particular thing you'd like to see by the end of the workshop? You guys want to chuck that in the chat? Like, the number one thing I'd like to see by the end of the workshop is, or say it. Comments.
So maybe, somebody I saw in the questionnaire asked about the sample quality, sample preparation. Do you want to say something about that? Like what concentration and, I mean, you kind of mentioned concentration in your talk, Greg.
Oh, you're asking me, or I thought you were asking our attendees. But is there sample preparations questions, like any logistic questions about how you get samples here? I think the rest of the afternoon right now, let me just chuck it up here.
Khaled had a question. What sorts of excipients are okay? I'm not sure what an excipient is. Khaled, do you want to elaborate?
I think it's sort of an additive, maybe. Usually it's typical. Okay. I have read in the literature, I haven't seen a lot of these experiments, but you can use urea sometimes to break up unwanted multimerization. I can see doing that. It's totally fine to add those things. Obviously, at some concentration, you're going to disorder your protein, and then you're going to be studying the disordered variant of the protein. But there's nothing about the SAXS that or the sample cells or anything that prohibits collection with urea or guanidinium. That's a great question. Jeff's asking about the pH of things and why in SAXS we have a request of being above 7.5. And that is because of the columns that we're particularly fond of, these Shodex columns. The matrix has a pH stickiness associated with it. So we prefer that. We haven't found any columns that can do the throughput equivalent to the Shodex yet. But it doesn't mean that we can't run with them. In other words, that if you had a Cephros or a column, that we couldn't run with those as well. You just need to make sure Mikkel and whoever's collecting the data, you need to discuss it ahead of time. I can't use the Shodex. I need to run my sample at 6, pH 6.
It's actually the reverse. You can't be 8 and above.
I'm sorry.
Yeah. So 6 is okay. If you run at 8.5, that's when you need to talk to them. Add that in your notes.
But I know we had this when I was there, and I'm not sure about the pH, but then the people just sent their own column, and we were measuring it with the column from them. So maybe this is
That's very true. So I think for the volume of the columns, the Shodex ones are 6 milliliters. And that, of course, is what you're going to dilute your sample by when it gets onto the column. And if you have a bigger column, that's the issue, right? How much you're going to dilute by.
I believe Dan has a comment in the chat.
Yeah, Jeffrey was asking about why we would like to keep the buffer below or equal to 7.5 pH for SAXS. And I think I read that the manufacturer of the columns suggests keeping it that way for like stability of the resin.
I think we've tested it, and I think the resolution breaks down above that, like its resolving power. But maybe it's breaking down the column, as you say. Other points. We could improve civils by doing this one thing. The SAXS program. Given some space here. Oh yeah, I was going to throw up
Why don't you talk about the person who was doing the lipid protein or lipid RNA? It sounded different than an LNP.
I think the person who asked, I think it was Valerie, she was asking about CRISPR.
Uh-huh.
So it's protein encapsulating RNA.
Oh no, it's not CRISPR. It's a protein that makes up a capsule. I have a question about the SAXS preparation. What if my protein have low concentrations that it can only reaches, like the highest I can reach is probably the recommended amount of the injection, so 20 microliters of 2 milligrams per milliliter. But then I've also seen that on the protein preparation, you said that we need to submit 5 to 10 micrograms per microliter samples for 1 milliliter-ish. What if I can't reach that concentration for my protein?
Yeah, so I mean, it's similar to the previous question asked, and one way to do it is to up your volume so that the milligram total content of your sample you're sending is higher. But again, there's a limit in terms of what we can, overfill the column with. So that's one way to go. The other way is to switch columns, and let's see, what else can you do? I mean, there's also the high throughput stuff, right? Which will give you better signal, but not the separation.
Yes. So the question I am facing is that I know my sample is definitely pure. Like I don't need the SEC column to lose the sample concentration once more. Is it possible that I skip the SEC part and then just go on with the X-ray beamline?
Absolutely.
Oh, okay. Thank you so much.
I'd like to sort of interject that as I said, the scattering is to square the mass. So if you have a large protein, then you don't need as much protein concentration as if you have a small protein. So what is the size of your protein that you wanted to do, Valerie?
Yeah, sorry, I opened my camera instead of my yes, the protein size is it's huge, so it's like 1,300.
Oh yeah. Greg, you want to say what concentration you need? If it's 1,000 kilodaltons?
Yeah. So yeah, again, in your case, right, because it's pure, you can let's see, mg per mil ratios. Let's see, how do I do this? It's mg per mil times kd should be roughly about 100. So if it's 100 kd, you can get away with 1 mg per mil, 200 kd, half a mg per mil, etc.
I see. Thank you so much.
So, Greg, Catherine said there was a question in the questionnaire that says, I want to learn how it could help with identifying my protein's overall geometry. You want to answer that?
So, I mean, SAXS is most powerful when you have an idea of what you're looking at, right? So it's sort of that constraints picture. There's a lot of different cases. If it's a multimeric protein, you have to apply certain programs as opposed to single chain. If it's got glycosylation or cofactors, there's other programs. My best suggestion, I think, would be to look in the literature for SAXS on something similar and just kind of see what occurred there. And we've got things like DNA PKCS, which is a megadalton size thing, a single chain. We also hold, let me make sure I got right. But so the other thing that you always recommend to do, and Susan went through it nicely. Sorry, I've got so many Zoom screens overlapping. Let me stop share because that's already complicating things. Susan went through a great example of using Fox. So ahead of time, calculating the signal you expect as before you send sample, and trying different geometries and throwing them into Fox and comparing the calculated SAXS signal from those different geometries. That will tell you whether SAXS has the resolving power to deconvolute those two possibilities. So I always recommend doing that. Calculate your experiment before you do it. In terms of publications, at our main website, Sybil's, we have a whole publication list for different cases here. And you could go, kind of look at what we've done in the past. These are all good examples of just look for something that's about the same size. Asking a similar question. Hopefully it's been done before. That's what I recommend. So it's noon here. This resource has a lot of, this sybils.als.lb.gov, BL1231.lb.gov has a lot of links to all our web tools, Fox, VoxDAX. There's a scatter download there. We try to highlight your publications as well.
Hey, Greg, sorry to interrupt. Can we take one more screenshot? Everyone, sorry.
Did you not make it?
PR. Yeah,
Okay.
I got, so there might be some new people in. So
Okay.
I appreciate it. I'll let you go after I take this screenshot.
All right, one last time, guys. If you could, all your smiling, lovely faces.
Yeah. Take a couple.
Last time that we asked. Sorry about that.
Couple more people. One more. Okay. Thank you, guys. Appreciate it. See you after your break.
When are we getting everybody out? 1 more hour from now? Or let's see here. We said at 2 o'clock, which is 1:30. So an hour and a half from now. So an hour and a half from now, we're going to restart. We have Lee June, Scott, and Dave speaking with room for questions at the end or practical course. So we'll see you guys in an hour and a half. All right, thank you.
Hey.
Hey guys.
Hey, thanks again for the invitation to give the talk. I hope it was okay.
It was great, Tina. Thank you so much for giving it and good practical application of SEC SAXS and the Bilbo MD.
Thanks. And it's nice to see your faces again. I
Yeah.
really missed the time. It was a great time, and I already talked to Lee. If I'm finished here, I'm definitely planning on visiting you.
Okay. Well, thank you. We'd love to see you.
Yeah, I'm really missing the time.
Yeah.
And the nice weather. I mean, at the moment it's nice again, but last week we had like 10 degrees, so really a flop from 30 to 10 and then up again to 30. So.
Good. LJ, you still here with us?
Hi.
Yeah. Is everything okay on your end with the talk and stuff?
I think so. Can I just try sharing my screen?
Absolutely.
What happens if I do this?
He's very pink.
Now it's live demo.
That's my background.
We have live demo now.
Okay, but is the resolution okay?
Resolutions, it's fine. Readable.
Readable. Okay.
Yeah, it's not like crisp, clear, like 4K.
What about this one?
Right now we see your presenter mode.
Oh, okay.
This
I think again.
Maybe I will share.
But it could be my my internet connection too that's just not sending.
Oh, maybe, but we'll see. Let's see.
This looks better.
This looks better, right?
Yeah.
Okay.
Yeah, it looks better than the other ones.
Okay. Sounds good. That's all I wanted to check.
Okay.
Then wish you a nice ongoing workshop.
Thank
Think I will leave now and maybe leave university and go home.
Yes.
Oh my
Uh,
gosh,
Because
yes.
I decided it's better to stay, because at the moment when you go home in the evening and everybody's using the internet, sometimes it's crappy and it's not working. So
Sure.
I still.
Thank you for doing it, and sorry to keep you up so late.
Oh no problem. But it's funny, I'm the only person left at university, so can't believe that people are really going home.
How far are you from your university? How far are you
It's
from
like
home?
not so far, because I have a subway which goes direct